All right, we're going to look at finance part 2, which is going to still continue to investigate savings, but in a little bit different way. So when we talked about the compounding interest, it required a large sum of money to deposit right away, and then you just kind of sit back and watch it grow over time. But a lot of us don't have that much money just put into an account so early on. So often what we'll do is we'll put like monthly payments towards something. Might be thinking about like in terms of like retirement, like every month you save a little bit of money. And so what this is called really, when you have this regular amount that you are saving every month, is a savings annuity. So we're going to start by thinking back to our compounding interest. And if we're looking at a current compounding period, PN, so we want to know what our amount of money will be here. Based off of the last compounding, so the one right before, so P sub n minus 1. Well, we're going to take the one before and it gets to earn interest. And so we're going to write this as 1 plus r over k. So remember that this is going to give us the total amount because the 1 is really getting your original amount back. And then multiplying your initial amount times that interest rate, which we're again writing as that periodic rate, r over k, because r is given as the annual rate, and k is the number of times that it gets to compound. So that's how we would calculate that. So with an annuity, so the same exact thing is happening, except that you're adding a little bit more money every month, and we're going to call that amount of money D. So what's going to happen is we'll have P sub n will be the last amount, and we'll earn some interest on that. But then we're also going to deposit some money. And so then what's going to happen is for the one after that, this entire amount of money will earn interest. So let's kind of look at an example to see this a little bit better without all the variables. So imagine that you're going to deposit $100 every month and your account pays 6% interest. So if you start with no money, so we're going to say that P naught equals 0. So this is your very initial amount, $0, okay? We're going to see that the account is compounded with the same frequency as if we make deposits. So if you deposit monthly, then we're going to say that it compounds monthly. We're looking at, again, P naught we already said was 0. Our interest rate is going to be that 6%, written as a decimal. Our K, because we're making monthly deposits, we'll say that our K is equal to 12, and then our D is the amount we're going to deposit each month, which will be the $100. And so if we want to kind of plug in some of that information, what we're going to say then is that P sub n is equal to P sub n minus 1 times 1 plus that 0.06 over 12 plus that $100. So that's kind of our situation, so you could see it with those real numbers. And so if we apply the same process each month, we're going to be using the recursive formula to find the future months. So it kind of restates what we have here, that P naught will be 0. And so then P1 is going to take that P naught times 1 plus R over K. That gets you that money plus interest, and then a deposit. So if the previous month had $0 in it, it's not going to have anything there to earn interest on. So it's just going to be $100. So we have that P naught is 0. So then P1 will just be that $100 because it was just that $100 sitting there. And so then it will compound the next time. So we could say that the next month we're going to have, again, P1 times 1 plus 0.06 over 12 plus that 100. But we know that P1 was $100. I'm going to start to simplify this. This is 0.005 if you put that into a calculator. So if I add that to 1, we're at 100 times 1.005 plus 100. And you can keep that as is for a little bit because what we're trying to find is some patterns. So if we do that same thing again, but this time looking for P3, we'll say, well, P3 is P2 times that 1.005, if we simplify that, plus 100. But again, P2, I'm going to rewrite P2, squeeze this in here. P2 was this right here. So we're going to have 100 times 1.005 plus 100. That's replacing the P2. And this is going to be all times 1.005 and then plus 100. And so we can actually kind of simplify that a little bit. Because that 1.05 is on the outside there, if I multiply it times this chunk and then this chunk, just distributive property, it looks like, I'm going to write it up here a little bit, P3 could be rewritten as 100 times 1.05 squared, because it would be times 2, and then 100 times 1.005, and then we still have plus the 100. So again, that's taking that amount, writing it with that product, and then also with that 100, distributing that. So if we do that again for P4, so P4 will be equal to P3 times 1.005 plus 100. Again, P3 we rewrote in this way. So we're going to write it in here, 100 times 1.005 squared plus 100 times 1.005. We just keep seeing the same numbers over and over again. That's why I'm kind of writing it this way, and it will help us to see some patterns. So that was P3. That needs to multiply times that interest rate, right? 1.005 with the whole, and then we're going to add in that deposit. Again, you could see that if we take that amount and we distribute it to, we have 3 terms now. There's 1, 2, 3 terms here. I'm going to end up that my P4 is actually equal to 100 times, we'll have 1.005 to the third power plus 100 times 1.005 to the second, because there would be 2 of those now. And then 100 times 1.005, and then plus 100. And so what I'm noticing, what you should notice something, let's think about that a little bit. I notice they all have 100, like each of those little terms in that expression, they each have 100. Then I also notice that the powers are decreasing. There's really a 1 there, but we don't normally write that. And so when it says, what do you think each term of the expression describes? Well, basically what's happening is that initial $100 that you put in, it's going to earn some interest. Then the next month you add in another $100, and that's also going to earn interest. But the original one will have earned interest twice. And then you get into month 3, and you can see that each of those hundreds has earned interest for a different amount of time. And so if you look in general here, you can see that their writing looks really similar. We got all these hundreds going on, and you can see that we have that 1.005 to the m minus 1 and then m minus 2, like they're decreasing, just like we had 3, 2, 1 here. This is just saying in general after m months. So we only went to P4. That was after 4 months to see what's happening. And again, you can see that after 4 months, it had this guy basically earning interest 3 times, and then 2, and then 1. And so what happens, what we can say kind of in general, we're going to kind of determine a little formula to help us out here. And you should take a couple minutes to read through this to try and make sense of what's happening. And then I could talk about that. So now that you've read that over yourself, you can see what's kind of going on. They took that expression from up above here and multiplied both sides by that factor, 1.005. And so what happens when that gets distributed to each term, if it was m minus 1, you're getting 1 more 1.05. It leaves us with just m. And so you can see that these are all actually 1 more than they were before because we had just put in that additional factor. Now, if we compare and line up this new thing we created by multiplying by 1.005 with the original PM from up above. Again, we lined up our like terms. And this is kind of a little trick, but it's kind of interesting that if you actually subtract these things, you can see all those things are going to cancel, and everything in between would have lined up and been canceling. And so we have that the difference between these will be equal to just our first guy and our last guy here. And 1.005 minus 1 whole will end up getting just 0.005 PM is equal to this quantity. If we want to solve for that PM, we'll divide by 0.005, and we end up with this expression here. Now remember, M was the number of months that we were actually making these deposits. And so if we replace that with 12N, where 12 is the number of deposits per year, like how we're talking about monthly, we could rewrite the statement in this way. And we can go even further, and let's talk about it in more general terms, using the variables that we're kind of used to, that the number of, or the amount of money for a certain number of years, and is it going to be in years, will be equal to your monthly deposits times 1 plus your interest rate over the number of times that you compound, which again, it normally matches up with the number of payments that you make, to the kn power minus 1. And just being careful with parentheses. This parenthesis here is times that whole thing, because it's how we factored that 100 out before. So I'm going to fix that just a little bit. And then this is all divided by R, just 0.005. That would be just the R over K. So this is our big formula that we're going to use when we want to talk about a annuity where you are making monthly deposits. So instead of that one time like we were talking about with compound interest, you're going to be making monthly deposits for a certain number of years. And again, I said monthly. It could be different, another different time format, but normally we make monthly payments because you talk about doing that monthly. You can also do it every other week, depending on how you get paid, and alter it accordingly. Okay, let's look at an example. We have Rosa and Angel. They're deciding that they should start saving for retirement. So they set up a tax-deferred annuity, which is also called an IRA, or individual retirement account. So here's the deal. They're going to arrange to take out $200 out of each of Angel's monthly checks. And the interest rate will be 8.75%. And because of that annuity, just a little side note, because it's deferring the taxes, he only notices it as $115 gone. So that's kind of something interesting that happens with your pay. If you are taking that out pre-tax versus after tax, it's kind of different. And if it's taken out after taxes, that's called a Roth IRA. So just a couple of words that you might have heard before. And so it says that we are going to, he just had his 30th birthday, and his annuity will come to term when he's 65. So we want to find out what that future value for the annuity is. So using that formula up above, we want to know what the amount will be after, well, what's the difference from 30 to 35? That's going to be in 35 years. So we want to know what's going on in 35 years. So the monthly payment that he said he's going to do is $200, and we're going to put the big parenthesis on there. We have a little parenthesis, 1 plus our interest rate, 0.0875 over, he's doing this monthly, that's 12 times a year. And this is going to happen for 35 years, so 12 times 35. And the formula has that minus 1 in it, so we'll have that. And then this is all over 0.0875 over 12. So when you go to enter this into your calculator, again, decimals is beautiful for this. Just make sure that this is the exponent, so you might want to multiply that out first. That might be helpful. And then sometimes people will put this whole denominator in a parenthesis as well. Not necessary if you're using decimals. Just make sure it looks exactly like that. And if you entered it all incorrectly, it should show you a balance of $552,539.96. And so that's the amount that should be there. So this is everything, all the payments he made plus interest. So if we want to find out really Angel's contribution and then how much interest he earned, let's think about his monthly payments. He's taking $200 every month. And so I wrote a 12 because there's 12 months in a year. And he's going to do it for 35 years. When we calculate that, it comes out to be $84,000. So he's going to deposit $84,000 over the course of 35 years. And that amount of money is going to give him hundreds of thousands of dollars. And that's all because of compound interest. So if we take the amount of money that he has in the account at the end, subtract off the amount he actually paid into it, we'll end up with $468,539.96. That's a pretty good return on his investment. That's how much interest that he would have. All right, let's look at one more situation here before we talk about our last thing for today, which will be payout annuities. Let's see, Ginny and Bert are having a baby, and they agree that they need $30,000 in 18 years. They decide to set up a savings account and have money deducted from each of Ginny's bi-weekly paychecks. So this means every other week. There are 52 weeks in a year, so that will mean 26 payments will be made. Now we're at a 9.25% interest rate, and so the periodic interest rate would have to take that as a decimal, 0.0925, and divide by 26. So this is how much interest it's going to earn every time it's compounding. And this time we already know how much they're going to have at the end, so we're going to start by saying, okay, we want $30,000. What is the amount that we have to deposit each month? So we're going to put our, we have a giant parenthesis and then a little parenthesis. I'm going to put -1. Whoop. And we know that we have 1 plus our periodic interest rate, 0.0925 over 26. And we're doing this for, it's at 18 years. So we're going to do it 18 years times those 26 compounds. That's how many times that it will compound over that whole time period. And then this is going to be all over the 0.0925 over 26. So now if I was entering this in my calculator, here's the deal. This entire thing here is a number, and it's being multiplied by RD, the thing we want to know. So if we want to solve for RD, we will have to divide by this whole quantity here. And so what that would look like, and it's going to look really messy. Again, you can enter it into decimals very nicely. So I would enter the 30,000, and then if you hit the divided by symbol, again, we're going to divide by that whole entire chunk. So this whole chunk here is going to be underneath that 30,000. So it'll have 1 plus 0.0925 over 26. And you might want to use the fraction button because this is a fraction underneath here with another fraction. Again, it doesn't look very pretty, but the calculator can handle that. This is 18 times 26 minus 1. So if you did enter that all correctly, again, sometimes people like to put the whole denominator into a parenthesis. You can do that. You could put the denominator of that into a parenthesis. That might be helpful, again, depending on which type of calculator that you're using. Now, it might take a little trial and error, but what you should end up getting is our D is equal to, it'll be 24.995038, which is really about $25 because it actually all rounds up. So if they make payments of about $25, then they'll get really close to that $30,000 mark, which is what they want.